we're located here in Ames, Iowa at Iowa State University. A few things I wanted to mention just off the bat is kind of boilerplate type stuff. Of course, if you haven't joined the audio conference, you're not hearing me talk. So, but if it does go away, you can hit the audio button, which is in the attendee panel. And what you have is panel icons up at the upper right if you're using a regular PC. It says participants, chat, and possibly one other one. What you want to do is use a chat pod to all participants, the drop down to all participants to communicate with me. I'll be tracking that chat pod for Chris as he presents in full screen. If it is full screen, these panels go away on your screen. There should be a little tab somewhere, depending on if you're using a PC or a Mac, that allows you, that'll cause a drop down. A menu will come out if you scroll to it. And you can pick the chat pod again so you can chat while he's presenting, and I'll be tracking that. If you've come on with a nickname or just a first name, please email me or chat with me to give me your full name if you intend to get a certificate. In fact, oftentimes we have multiples of people with first names. Hussein, I just actually sent you an email. We actually have more than one Hussein in our registration list. So you're going to want to send me your last name if you'd like to get a certificate. If there are other people in the room that are going to be watching that haven't been registered, certainly send me a chat or send me an email and let me know about that. Again, it's all participants to communicate with me and everyone else at this time. We have weekly or bi-weekly online webinars through Iowa LTAP now, and next week on the 23rd we will be talking about work zone safety, temporary rumble strips, smart boards, smart arrow boards, excuse me, and other connected technologies, traffic control technologies. On the 31st, I'll be doing an ethical choices, what would you do hour on the 31st. Again, these are at noon Central Time. And on the 7th of August, we have one on working with heated pavements, recent technical advances. And in August, we then will be taking a break to take a breather to plan for the fall, but we do fully intend to have, in cooperation with the Institute for Transportation, provide bi-weekly webinars again, with my idea being both Iowa national and international speakers, because that's just the wonderful thing and opportunity about virtual, right? Can find anybody in the world and they can hook with us and we can learn something during lunch or an hour before or an hour after, I guess. In addition to in the fall, we'll have some virtual regional meetings where we're trying to work those out, smaller meetings, outdoor trainings, that kind of thing. Last but not least, a couple other points. A lot of you are from other states. We are an Iowa state-based program. We do not go out and get pre-approvals for our courses and things like that. So if you are a PE and need these PDHs, this certificate that I provide may or may not be of any value to you, depending on the rules in your state. So just understand that because, you know, again, we're a state-based group where we don't track PDHs for people. Last but not least, if you are what we're now calling a webinar pirate. Webinar pirate is someone that gets the link and doesn't register. And that's all great and wonderful and welcome. I appreciate you being here, but there's absolutely no way we can tell who you are if you don't register. And it's fine that you're listening in, but if you intend to get a certificate, the only thing that WebEx can track is the people that are online with their real names, and we can tell whether when you come on and off and that kind of thing. And for now, that's what we're willing to provide people a certificate of attendance on. May change as time goes on, of course. We are recording. We do post all of our weekly webinars on our website. You have to fill out a little form, tell me who's watching it, kind of how many people might be watching it, and you're good to go. So without further ado, I am going to make Chris a presenter, and we'll see if his sharing power has stayed. Chris is an assistant professor at Iowa State University, civil engineering. Prior to joining Iowa State in 2017, he worked at Purdue University as a research scientist for about 7 years. Chris is a key researcher on automated traffic signal control performance measures, having been involved with several projects for Indiana and Iowa DOT, NCHRP, and Federal Highway. He holds a PhD from Purdue University and is a registered PE in Indiana. So he's now doing full screen. And if you want to get your panel, go up to the blue tab and hit the little chat pod panel, and you should be good to go. Chris, I'll be tracking that for you while you present. Go ahead, Chris.
Okay, thank you. Are you able to hear me?
Yes, you're going to want to take your mouse from the drop-down menu so it disappears, because it's crosshatched now. There you go. Thank you.
Okay. All right, thank you. So thanks everybody for joining today. So again, this presentation will be on the topic of automated traffic signal performance measures, a local agency perspective. So what I'll try to cover in this hour will be, first of all, some background on what are automated traffic signal performance measures, what's the motivation for, how did they arise. I'll talk through a couple of examples in some detail just to show a couple of applications of these performance measures. I'll talk briefly about benefits and costs of this technology. We had a recent study with Federal Highway where we tried to come up with a methodology to estimate those things, and then I'll conclude by talking briefly about how to get started from a local agency perspective, just a few thoughts and reflections on some of the things I've seen in recent years. So in the past couple of years, about 2016 through 2018, into 2019, there was a series of workshops that Federal Highway sponsored. I don't know if anybody on the call was able to attend any of those. Some of this presentation will repeat some of that content, but I'm going to try not to repeat too much, but I wanted to include some of that material for anybody who hadn't seen it previously, because to my knowledge, I don't know whether this has been featured in a lot of LTAP content. But so some of this may be a little bit of repeat for some of you, but I'm going to try to have a little bit of building new stuff at the end. So just a little FYI there. So let me just jump right in and give a little bit of background on what ATSPMs are, where they came from. So going back to a lot of the research that we were doing at Purdue while I was there, some of the motivation that we had at the time was, and there was this realization in about a decade ago that there was a need for better traffic monitoring in signal systems. So there was this effort to do a national traffic signal report card. There were a few versions of that came out, and different aspects of system operation were considered, but one that consistently came up with a really low score was the category of traffic monitoring. So there was, clearly this need to try to improve the way that systems were being monitored. And then from a practical perspective, just being able to get intelligence about a large number of signalized intersections, looking at level of effort for managing these types of systems. Again, this is from a DOT perspective, but back in Indiana, our main research client was Indiana DOT, and they had to manage 2,300 signals across the state with a staff of about 4 or 5 people to try to maintain signal timings, and then it's kind of similar situation in Utah. And so being able to go from the idea was there was this need to try to get information about how these things were operating on a day-to-day basis, and that was kind of the goal there. So if you think about one particular corridor, if we just grab an example location, we went through at one point and tried to, just looking at the types of controllers that happened to be out in the field in this location. We did a little study to see how many parameters actually were, existed in the controller. We found that there were 74,000 total changeable parameters if you just considered every single thing that you could potentially change. Up to about 260 of them would actually need to be set up to create a typical coordination plan for multiple times a day and so forth. So scale that up to a whole corridor, and you've got thousands of opportunities to make a mistake, right? And so, just kind of reflecting on the practical need for some kind of monitoring, it would be really useful to be able to see those kinds of things at a broad, getting that out there in a scalable manner was kind of the idea. So this concept of high resolution data emerged about the same time period. The basic concept is that we're trying to keep a record of events at traffic signals, and these would be written down as 1/10 of a second resolution, which is the same time resolution as the signal controller. So what do I mean by event? I'm referring to things that have some kind of electrical impulse, if you will, in the controller. So detectors turning on and off, phases and overlaps changing their states, green, yellow, red, PED buttons getting pushed, the PED signal heads changing their state. Pattern changes could also be written down, so transitioning from one pattern or action plan to another. Cycle offset split adjustments by adaptive control, if you've got that, those kinds of things could be recorded. Phase, omits, transit signal priority events, preemption events, and so on. A railroad crossing gate down, just anything that occurs that has some kind of record in the control system or some kind of a state. Those state changes are what we're referring to as events. And so over the course of the previous decade now, about the early 2010s, kind of feels weird to say that now. We had some discussions with different folks in industry, different stakeholders on what that data ought to look like. And, Indiana DOT kind of kicked off that process, and ultimately we ended up with a set of enumerations for these events that has been more or less agreed upon and implemented by the industry. So, so there's a document that contains those definitions, and this is just a glance at what that looks like. So you've got phase events, things like the phase turning green, yellow, red, and then some other kind of hidden sort of things that you would sometimes see, and then detector on, detector off. So there's just a few examples of what those events look like. And then, so the raw data, if you were to take a sample of that, could look something like this. So, for example, let's suppose that, I've got a listing here of all kinds of stuff going on, but if we were really interested in, say, what happened to phase 8 at this particular time of day, and suppose that for this example, detector number 5 is the only detector that drives phase 8, we could say, okay, at a certain time, we see that detector turn on. A little bit later, we see the phase turn green. So, we see a call come in for the phase. It gets served. The detector turns off, so the traffic has gone and disappeared, and the phase turns yellow shortly after. So, very microscopic view here, but the initial use of this data was to evaluate detection systems. So we would go in, the question at the time, back in the early 2000s, was, okay, if we had video detection, does it provide the same, record of what was happening as loop detectors? So what they did was they would co-locate to the systems and compare in a detailed way when the specific on and off times would occur and all that kind of thing. Well, it was quickly realized that the same data set could also be used to calculate performance measures. And so the very first round of performance measures were based on those kinds of quantities that you would need for a highway capacity manual analysis. So your volumes, green times, so forth. And so I'll talk through just an example of what that sort of calculation looks like from a raw data perspective. So, suppose this is our timeline of the phase events as they're occurring. The events themselves would be these kinds of records. So we would see event code 8 for the start of yellow, event code 10 for the start of red, and 1 for the start of green, and so on. So we can establish a record of when a phase is in a particular state. We could also keep track of vehicle counts or something like that. And in some of the examples we'll see in a minute, we're looking at occupancies and so forth. But in this case, suppose we want to just get the number of vehicles that were served by this phase. Let's suppose this is a stop bar detector, so maybe we've got some kind of system that can do a count analysis. In Indiana, it was very common to have a loop detector with a special amplifier to provide a separate count output. So we might see the first 2 vehicles show up in queue during red, then you wouldn't see anything else until the start of green, and then traffic would start moving. But at the end of the day, or at the end of the cycle, I guess, we would see how many vehicles went through, or a good estimate of the total number of vehicles that happened to get served. So we can figure out the duration of green from those phase events, 44 seconds in this case. If we make an assumption about the saturation flow rate, then we can figure out, okay, if there's, if this is our capacity, then we have a capacity of 23.2 vehicles. We count 17 vehicles overall. So if we take that volume, divide it by our capacity, we get a volume to capacity ratio of 73%. And so this is just one example. And so kind of going back to this slide, you can develop this picture, as you can see here, of what that volume to capacity ratio looks like for individual phases and so forth. And all that kind of stuff is possible. Now, what I wanted to show here are just a few more examples of things that go into a little more detail and are maybe closer to, two aspects of operation that we can kind of take a look and scale up to a high level. So, so where to begin? So when in discussing this, one thing I kind of like to show is this cartoon that I happened to find when I was doing lit review for a thesis a long time ago, but well, it wasn't as long ago as when the cartoon was, but I happened to come across this, and it's kind of an interesting picture where you've got 2 intersections, both under police control, and there's kind of quite a bit going on. It's a nice multimodal picture with the trams and that sort of thing. But you've got the 2 essential problems of signal operations that are occurring here, and it's really the same problem we face today. One is, how do we distribute capacity locally, and how do we deal with progression? And so this was sort of our starting, and those concepts are reflected in the highway capacity manual delay equation. I'll skip past this and kind of just show the big picture perspective is that we came up with when developing methodology for performance measures, is to think about this hierarchy of how things work in the system. So first of all, you've got to maintain the system in order to make things function well, so getting your detection systems and your communication systems to work properly so that you can actually measure things and get the data back, and also, of course, operate the actuated control of the system. Then you have this concept of the local timing, which is dealing with the capacity distribution, making sure you have adequate green time on each phase, and then the system timing being a layer that is a little bit above that. So assuming you get that local control to work well, how do you synchronize multiple intersections to achieve goals such as a common one being, okay, do I have most of my vehicles arriving on green if you're dealing with coordinated operations? And then, of course, you might have some advanced applications. We kind of have this cherry on top of the whole thing as kind of our example of that. But what I'm going to focus on today are really these 2 questions and pull out a couple of example performance measures that dig into those in some detail. So the first one, do I have adequate green time on each phase? If you look at, I showed volume to capacity ratio as an example earlier in detail. Another thing we could examine is a record of the amount of green time being distributed to individual phases. So this particular example shows a view from the open source software that was written by Utah DOT, and they have what they call a split monitor. So this shows the amount of green over the course of 24 hours, and we can see the duration as well as the reason for the phase termination. So whether we gapped out or maxed out or forced off and so forth. And so we can see things like, the variability of green during a particular time of day. For instance, this phase has anywhere from 40 to 70 or so seconds of green during the PM peak, for example. We can see occasional max outs during this portion of the day where we kind of drop coordination and run fully actuated and so on. We can see occasional PED activity here and there, and then constant PED call being displayed or being given during the coordination. So we can see a lot of detail in some of these views. Now, detail's fine, but another thing we wanted to try to do is come up with some measures that would be easy to scale up to some aggregate view at a high level. And so one thing that we worked, and another issue that we kind of contended with when we were developing some of these things was the variability and the sort of detection types that were out there. And so we wanted to come up with something that, for the capacity side, would be more general. And what we ended up with is an analysis of occupancy of stop bar detectors to determine whether or not a split failure had occurred. So split failure, cycle failure, kind of those terms get thrown around, but basically you have instances, and we'll see an example in a minute, instance where you have inadequate green time. And so back in 2013, we had a really good location where we had an example that we could look at. And if you go to this intersection now, you'll find that it's been completely grade separated. So if you really want to get rid of your signal operation issues, you can get rid of your signals altogether. But at the time, this was, a pretty busy site, and it was a great place for us to go and get some data to test out some of these measures. So what I'm going to do is just show a couple of examples in some detail. So what we're going to look at is we'll be paying attention to these two through lanes. So you've got a through lane and then a through right shared lane here. In this is the eastbound approach. We can see the westbound signal, so it kind of roughly corresponds to when this arrow goes away. A few seconds later, it turns green for them, right? But we can also look at, we'll be tracking the phase state here as well as the occupancy state of these two lanes, of stop bar detectors in these two lanes. So I'll just go ahead and advance this and we'll see what happens. What we're going to try to look for is the back of this queue at the start of green. So you can see the arrows come up. It's going to disappear here in a moment. And the back of the queue is right about here. So we have the start of green, traffic is moving forward, and you can see that pretty much all that traffic that was initially queued up managed to get through, and here we've got the end of green, and now there's a couple of vehicles left over, but they kind of arrived a little bit later. Now, if we look at the record of the occupancy here, we could say, okay, what was the percent of time that these detectors were occupied during green and during this initial portion of red? Well, those values work out to look like this. So the green occupancy ratio, or the percentage of time that we were occupied during green, is pretty high. This red occupancy ratio during this first 5 seconds of red is relatively low. So anyway, in this case, this is not a split failure because we managed to serve all the traffic. Now, another cycle at another time, a little bit later or a different time of this same day, you can see here, this is the start of red. We've already got a pretty extensive queue that's already back as far as this little driveway coming in out of the strip mall here. Go ahead and play this one, and we'll see that, the situation here is somewhat different. There's quite a bit more demand. In the back of the queue is all the way back here. I think you can probably guess what's going to happen is not all those vehicles are going to be able to be served. Spoiler alert, but we can see that, okay, we've got our green, a lot of that traffic was served, but we really didn't have any chance to serve everybody. And so what do the metrics come out looking like for this cycle? Well, they work out to be that, our occupancy is pretty much maxed out during both the whole green as well as the red here. So if we look at how that looks over an entire, portion of the day, so this was kind of a midday time period that we looked at, we can analyze the green occupancy ratio, we can analyze this red occupancy ratio of the first 5 seconds. And so if we have a high value of the green occupancy ratio, it means there's very few gaps in the traffic. That by itself is not necessarily a bad thing. It could be that you're just utilizing all your green, which is actually, you don't really want to have wasted green. So having a low green occupancy ratio is not necessarily a great thing either. But what we kind of want to avoid is having a lot of unserved vehicles left over. And so this red occupancy ratio helps us to measure that. And so the two example cycles we looked at kind of show up here if we plot those in this diagram. And after considerable analysis, meaning after we made a grad student stare at a lot of video of traffic, we found out that about an 80% threshold seemed to work pretty well for determining when a split failure would occur. So we can go from this very detailed view to a single number of how many times do we have cycles that were up in this quadrant, and that would that tells us the number of split failures that occurred. And so we could take that number and start to do analyses like this. So this is that same intersection. This chart shows the number of split failures before and after we made a little bit of a change to some of the splits out there. So we ended up taking a little bit of time away from phases 2 and 6. We gave that time to phases 3 and 8. And as you can see, the number of split failures was reduced by a little bit more than half in both cases. So there's just a couple of seconds of split time, transferring that around, we could immediately see the impact. Well, not immediately, we could see it, one day after it had operated, we could calculate the number and see the impact. And to explain, for phases 2 and 6, we didn't have stop bar detectors, so we could calculate, but we did have step back detectors. So rather than trying to do occupancy, we would do a count and then calculate volume to capacity ratio. A long story short is that the needle didn't move very much for these phases, but we did see a pretty good impact for these other ones. We could do other analyses with the same data. So this is just an example of a location in Utah where they had put in a adaptive cycle length, system. I don't know what they call it. They kind of developed their own system using a lot of interesting custom controller logic. That's this long story I won't get into, but the point is that they had this corridor that was very, very far away from Salt Lake City. They had no way to send people out there easily, so they came up with this system that, and of course they had lots of, variable demand with national parks in the proximities. This is Moab, Utah. And by making the cycle length adaptive, they were able to reduce the number of split failures occurring at these intersections in the middle of this town by a really wide margin on the major street, and then the minor street didn't get affected too much. There's not a whole lot of change. But this, big decrease was able, kind of one way to verify that they were getting kind of what they wanted out of the system. And we could also apply these kinds of analyses to look at corridors. This is just an example. We can see, okay, along this corridor, there's 10 intersections here. It's very clear that most of the problems are occurring up here at the north end, where there's this mall, and we've got the mall entrances, and actually we can see which movements are the ones that are contributing to the most problems. So clearly this westbound left turn at this particular intersection is problematic. And so if we wanted to decide where we should spend effort in doing retiming, that would be an example. And we can do the same thing at even higher levels, going up to several corridors across the system, and so forth. In the interest of time, I'm just going to speed up a little bit and kind of make sure I get my second example in, which is for coordination. And so the traditional approach is to use some kind of modeling. So you would make your assumptions about the speeds and the volumes, plug those into your favorite model, run those, and say, okay, well, the model says my coordination is good if I use these offsets, and so forth. If we had perfect information about the system, we might get a picture that looks like this. This shows all the trajectories of vehicle movement. Now, this is actual real data coming from this NGSIM project, and it took them a whole lot of effort to get all of this data for 10 minutes or something like that. So not a very scalable approach. Maybe one day when we have 100% connected vehicle fleet, we would be able to see this, but we're not there today. And so what we do have today, though, is the detectors that are out there in the system. So if we do have a detector, we could measure times when vehicles cross that detector, and we could relate those to when the signal is red and when it's green. And we could develop a picture that looks like this. So for a single cycle, we can see when those arrivals occur relative to when the signal is green or not. So from that, we developed this concept of what's called the coordination diagram. And I'll just show this video that kind of explains it. So we've got detectors here, and as vehicles are crossing those detectors, what ends up happening is you'll see dots that show up in this diagram. So what this is showing is we have time of day on the x-axis, we have time in cycle on the y-axis, and then the coloration is reflecting the signal state. So we have start of red. So we start at the beginning of the cycle, it's red for a little while. In this case, yeah, we see some vehicles show up. It'll turn green here in just a moment. And any minute now. And then we have that's reflected in the diagram here, and so we have a few more vehicles show up after that, and so on. So this, picture, we're starting to see, this is microscopic detail, but again, we're getting this record of what's happening there in terms of the signal coordination. If we look at those over time, that we can see whether patterns emerge. And so in this case, this is not the same site, but we're looking at about an hour here. We see each one of these columns, if you will, is an individual cycle. This portion of time down here is when it's red. This shaded green is when it's green. And the clusters of these dots reflect when vehicle platoons are coming up from the neighboring intersection. And so we can find the total number of arrivals in green, the number of arrivals in red, and calculate a % on green. And so we can expand that out to, say, a 3-hour period, or even to an entire 24-hour period, and we can kind of see patterns emerge at a high level. So we can also see anomalies in the data. So this is kind of an interesting one where we have these kind of weird patterns emerge. So in this case, again, these clusters of dots that are kind of, repeating throughout a time period are kind of showing that, okay, during most of the cycles, we've got platoons showing up and they're being served in green pretty well, and maybe during this time of day, it's not so good because we're serving the other direction, so this is a very typical inbound versus outbound type of pattern. Then we have some other weird things that kind of show up, and we can see this is a particular example where if we look in detail, we can see that the platoons are arriving earlier and earlier and earlier in each successive cycle. And what this is caused by is that the neighboring intersection is running a different cycle. Now, we don't know which one is the right cycle length, but we know that somebody made a programming error, and this is something that jumps out with the data pretty quickly. Just kind of going through these a little bit quickly so I can make sure I get through all my slides at time. And I wanted to show one example, or a couple examples. This first one this is State Road 37 in Noblesville, Indiana. We did a study on offset optimization using these 4 signals at the time. This is back in 2010, so we're almost at a 10-year anniversary. This is kind of hard to believe. Actually, even this data is a little bit older than that. But looking at a high level, if we look at the whole corridor, we can, if we were going to be going northbound on this corridor, this is during a Saturday, so the plans run from 6 a.m. all the way to 10 p.m. So that was just kind of how it was done for Saturday on this corridor. But this pattern had been put out there, and nobody had really taken a good look at it because it was on a Saturday, and kind of typical weekend plan doesn't really get that as much attention as the weekday plan. So when we first looked at this, we discovered that if we were going northbound, what would end up happening is we probably have to stop at this intersection here. The next intersection, we probably make it through green. The third intersection, we probably have to stop again. And then that fourth one, we probably get through. And in the opposite direction, you have random arrivals at this first intersection because it's more than a mile to the next intersection up. Then we probably stop here, and the rest of it is pretty good. So this is before optimizing the offsets. And afterwards, we can see that we were able to get a little bit better. And so, again, if we just pay attention to northbound, you can see that we've shifted those arrivals up into the green. And so if we go back and forth, this is kind of like when you go get the eye exam. If you have glasses and they say, do you like number 1 or number 2 better? Well, number 2 is a little bit better. So visually, we can see these things in detail. we can also summarize those in terms of that percent on green number. So if we compare it before and after, we found that we got big increases in the percent on green on those approaches that shifted from red to green. So these two kind of correspond to these big dark green chunks. And we got a little bit worse in this direction for this one, because not everybody is always going to be a winner when you're doing two-way coordination. And we could confirm that with a separate travel time measurement. So I'll kind of just jump to the conclusions here, and just kind of what we saw was that little change got us a 2-minute improvement in travel times in the northbound direction, and really no harm done to the southbound. I'll kind of just gloss over and say, we did the same study about a year later. We were able to see if we took those changes in travel time and annualize those, we realized about a $500,000, benefit for the Saturday plan alone, just to kind of show that. And then we did a few consecutive studies on this corridor, and then every time we went out there, we would calculate the user benefit, and we got a number, a pretty decent number, about $4 million if we. By continuing to do this over a 5-year period, just going out there and periodically updating offsets. So I'm going to, just because we're 20 minutes left, I want to make sure that I get to my other examples. I'm going to skip over this one just because I don't really quite have enough time. But an interesting case study, if we share the slides, you can take a look at that. And all this stuff is in some reports I'll present at the end, links to those. But I want to talk briefly about benefits and costs, and then talk a little bit about how to get started, because I feel like that's the more, that's kind of the newer content here that I wanted to get into. And so, so we had so kind of reflecting, I've actually just told you about this in the previous slides, but there were a couple of studies that we did in Indiana where we did some analysis of changes in travel times on corridors related to signal timing changes that were facilitated with use of performance measures. And each one of those, the annualized benefits came out to be, user benefits came out to be some fairly significant numbers. So we had a study that Federal Highway sponsored. This just wrapped up this in May. And so the report for this should be coming out sometime this year, I hope. And what we try to do here is we try to develop a methodology for quantifying or helping estimate benefits and costs of an ATSPM implementation. So the idea being that, ATSPMs are a tool that you can help, discover and resolve some unknown problems, and if we shift to proactive use of the data, we can sustain some benefit. And so what we did in this is we tried to come up with a methodology that would allow for some flexible, that the user could flexibly select which categories are relevant to them, apply that to a multi-year life cycle if they wanted to, and then decide whether the investments being made were being attributable to the ATSPM effort or to other efforts. And so we much more detail obviously in the report. I just wanted to talk about this for a minute and kind of give kind of our results at a high level. So what we did as part of that study is we talked to 6 different agencies as case studies, and I just wanted to kind of show the overall conclusions from that. And so 3 of those agencies were state DOTs, and the other 3 that we talked to were local DOTs. And once we had kind of gone through and interviewed individuals at those agencies, kind of got some estimates of what they had spent to implement an ATSPM system, and then we kind of talked a little bit about, okay, what sort of benefits were they seeing in terms of, one, shifting, reduction of time that they're spending on certain tasks, or, in some cases, whether they were able to see user benefit or not. These are kind of how those numbers worked out in the end. And these numbers are reflecting, they're scaled up to a 10-year life cycle, which we had assumed in the way that we went through and executed the methodology. But as you can see, just as a few examples, the benefits generally, the payoff being quite a bit higher than the cost in most of these cases. As you can see, there's one agency that we didn't have enough data to estimate a benefit yet, but this is kind of what we saw there in those case studies. A couple of examples. One, Utah DOT is a really unique situation since they have invested all this effort to implement the open source software. So they had, these really, high costs of what we classified as installation, but I was really developing the system. They had something like 10,000 hours of time into that. But, since they did that, nobody else has to if they wanted to use the open source system. So they're kind of in a unique situation. But their payoff, however, was pretty significant. So they were able to reduce the amount of time they were spending doing things like manual data collection and responding to public complaint calls. And that by itself was enough to outweigh the investment in their system. But in addition to that, they also we also estimated what they, a very rough estimate, but what some of the public benefit might have been in terms of travel time or delay reductions in certain categories. So responding to the fail detection faster or improving the operations a little bit. And so the overall number there, for about $2 million of investment, they got about $108 million of benefit out of that over a 10-year life cycle. Now, one caveat, to this analysis, we tried to consider, okay, how much does it actually cost to make use of the system, and so that kind of comes up as a separate number. So, but that's really kind of, okay, what's the number of hours that you're spending using performance measures rather than what you used to do? But that's not an upfront number that you have to come up with. That's just like, okay, how much time are you assigning people to actually work on signal timing using this stuff after you've got it? Anyway, another example from Maricopa County, which kind of a local agency example for them. Their upfront kind of out-of-pocket, if you will, investment cost for something like $75,000. So they had, a consultant that they hired to install the open source software, and they procured a server, and that was really what their cost was. Now they did make some investments into their detection systems, but since that had already been done in a ongoing effort that was considered a sunk cost, meaning that money had already been spent, even though it was definitely beneficial to the effort in putting in performance measures. So, you could pick which of these numbers you wanted to consider, that which you'd have to come up with in terms of new money or that much had previous investments, and then effort to actually realize the benefits later. But a rough estimate just in terms of shifting efforts away from manual data collection and schedule maintenance, response to complaint calls, the benefit is about $1.5 million is kind of what we saw over a life cycle in this particular example. So these are just a few highlights of that report, just wanted to pull out. A few findings that we saw from that study is that most of the agencies we talked to really didn't have a formal planning process. These are some of the earlier implementers, so they just kind of jumped in and got started. But we did see a lot of variety in terms of the numbers of signals, anywhere from 50 to 5,000. So I think Georgia DOT was the largest one there. We didn't see a lot of tracking of quantitative, costs and benefits. There's a little bit of information we found, but not a lot of detail. And so, our methodology is a little bit of a stab in the dark because there's not that much data that's been collected so far. But we did kind of come up with at least a starting point to be able to, pull figures in and come up with a number at the end. We saw a variety of approaches being used, and most of the agencies we saw had good executive support. I'm just going to kind of jump into the last topic just to fill up, because I've got 10 minutes left here, and because I do want to get through this. I think it's probably the more relevant part to those maybe in attendance today. So how do you get started? And so what I'm going to just kind of go through here is, first of all, can you understand the process would be, okay, one, understanding the parts of the system, two, assessing the current readiness of the infrastructure and the institution that your agency, identifying opportunities for collaboration, and then finally choosing an approach that's appropriate. And so understanding the parts of the system, I kind of want to take just a minute and clarify, again, what ATSPMs are, because this is a point that comes up every now and then. People aren't too familiar, or who aren't terribly familiar. I think some of this stuff gets conflated with other things. And, the ATSPMs that we're talking, the stuff we're talking about today is based on this high resolution data. And that type of data can be obtained from a lot of existing signal controllers, and then there's external devices that can obtain the same data if you're using an older controller that can't be upgraded or replaced. But the main point I wanted to make here is there's really not any requirement to have any kind of connected vehicle type of technology to do this. It's something that can be added into a lot of the existing systems. That's something that every now and then somebody has questions and they kind of overlap the two a lot. So the main point is that ATSPMs are kind of made for logging what's happening at the intersection and kind of taking a look, some time period later. So it's that they kind of fill a particular niche, if you will. So what do you actually need to run the system? So, okay, one is having a device for data logging. So as I mentioned, a lot of controllers can do that. There are some external devices. Sometimes all you need is to upgrade the firmware to make that happen. Two, some communication to the controller to retrieve data is really useful if you've got that. Sometimes you can do offline type of retrieval, although it's not meaning that you let the data collect locally. You go out and get it every now and then. So if you don't have communication, that's kind of the other alternatives. Obviously not the preferable one, but nevertheless it can be done. Detection at the signal is useful, and so existing detection can often be used. But what you really need to have is that mapping of understanding what the detector channels are relative to what phases, and then finally a system for actually producing and delivering the performance measures for which there are a variety of options. And I'll talk about all these things in a little bit more detail. If we think about, assessing current infrastructure readiness, I mean, this is kind of, okay, we want to think about it. How ready are you to go out and implement these things? I try to just collect a few thoughts on that. Okay, so what are the three main pieces of what you need out in the field? One, the controller, the communication system, and then the detection system. So from a controller standpoint, either, if you have a lot of existing equipment is compatible, so, maybe you've got controllers that already support the data logging, maybe they just need some kind of firmware upgrade or so on. But, on the other hand, if you have a lot of legacy equipment that's not going to be so easily adjusted, then you may have to procure new stuff. In terms of communication, in the most ideal case is having a lot of good stable communication to all the intersections. Maybe it's a little bit more sporadic, so you might fall somewhere around, these kind of spectrums. And then detection system, I've got another slide that talks about this in a little bit more detail, and so let me get back to that one. Communication systems, we've seen a variety of things used out there. Utah DOT had the foresight to, over the years, prior to even before they were thinking about ATSPM, they've leveraged their right-of-way to get fiber links out to most of their locations. But more typically, we've seen things like cellular modems and other geographically distributed things, and then as a last resort, what we might call sneaker net or something like that. Again, like I said, logging the data locally and then retrieving it occasionally, more or less going out to get it. Now, detector layouts, this is a question I get quite a bit, and I kind of came up with 4 archetypal patterns here, and I've seen examples of all of these. So, I won't, for lack of time, I won't go through each one in detail, but I would say most agencies kind of fall somewhere in between these 2 middle categories. There's not too many people who don't have any detection at all, and if that's the case, you can look at the phase timings. That's really all you can see. On the other end, you don't see too many agencies out there who just love detectors so much that they just have saturated their systems with them. But kind of most agencies fall somewhere in here. So they might have some cases where, okay, I've got phases 1 through 8, I've got channels 1 through 8, so I'm going to plug in directly into that. And so, or maybe they say, well, I want to save a, you know, incremental savings, and don't put detectors out on the phases we're going to recall to anyway. So if you're on that side of things, you know, you can get some useful information. You can at least look at and see how frequently you're maxing out, forcing off versus capping out, those kinds of things. But reconfiguring some of those zones would be kind of helpful. So if you've got radar or video, that's relatively easy to do. On the other hand, if you've got, you know, you've taken a little bit of time to develop maybe a pretty good layout, maybe most of your lanes are represented, perhaps not every single one of them. Maybe you've got lane-by-lane detection in some cases, perhaps not all approaches. Maybe you've got setback detectors. I mean, I would say a lot of agencies kind of fall in this category where they've got, you know, kind of a layout that works fairly well. And for performance measure reasons, it probably works really well for actuation. I would say this is a pretty good setup for doing performance measures. So my point is that a lot of the existing detection can actually be done. And if you go back and look at some of the early adopters, you know, some of the state DOTs, Indiana, Utah, they really didn't have to do a whole lot of adjustment to be able to do performance measures. And in fact, in Indiana, they just used what they had. Institutional readiness is a whole other topic. I won't spend a lot of time on this just because there'll be a report coming out here this year. I think they'll talk about this in a lot more detail. But basically, just another dimension to consider. And I want to talk a little bit more about, okay, do you have these people around or not, right? So the question is, okay, yes or no. So a signal operator, meaning the engineering staff or whoever is actually managing the signal timing, does that person have an interest in APSP? And that's kind of the first question. Like, well, yeah, if they do, then you have a reason to actually proceed with trying to procure or implement. If not, then, you know, maybe it's not the best use of time. Of course, the question would be, okay, why are you even here if you don't have the interest, right? But that's, you know, the first thing to think about is, okay, is there going to be somebody who's going to actually use it, right? So you want to put in technology that's going to be used. So the second question, kind of getting into how you're going to do it, is one, do you have an IT resource, you know, for managing the service? So do you have an IT resource? First question is, do you have an IT resource? And maybe the second question is, do you want to use your IT resource? So if you've got that person and you like working with them, you can say, okay, yeah, we can manage operating our own server. We're big enough to do that. If not, then you might want to consider another option. Maybe you go to a vendor, see what kind of product they have, or maybe you find another agency to collaborate with or something like that. And then the third thing maybe that we can talk about here is whether you have support from executive staff, meaning do you have somebody who, you know, can figure out how to get money from them or get their buy-in on, okay, if we use this technology, we're going to be able to get some benefit. And so if you do have that, then you can take a more top-down approach, meaning, okay, we can find money to spend. If not, then it's still possible to work on this stuff, but it's from a more of a bottom-up approach, so that incremental building capability to the system. So I think when we talk about technology, oftentimes we think about big capital projects. We're going to go and spend $1 million to make this happen. But if you look at how this was actually done in Indiana, it's kind of the first state to kind of roll this out, we really didn't have that at that kind of perspective. We were building, you know, trying to think about, okay, you know, one intersection, one corridor at a time, upgrading the controllers, kind of adding them in, kind of organically growing the capability. So you know, they did things like adjusting their specs so that new controllers can handle data logging and so forth. So there's alternative approaches to doing this. Let's see, a couple minutes left to kind of get through this last little bit of content. So, you know, another thing you can consider is whether you have opportunities to collaborate with other agencies. So maybe there's other locals in the region, maybe able to share resources. So an example of that, back in Indiana, Elkhart County and the city of Mishawaka, which is in a neighboring county, kind of pooled their resources together to make use of a system that had already been deployed in Elkhart County so that Mishawaka could see the data from their side. So that's just one example of kind of a collaborative effort. You know, friendly situation, no, you know, no major agreements or, no like kind of legalese stuff that went into that, just kind of, hey, we could use some help, do you want to help us out, and that kind of thing. So if you've got that kind of amicable situation, that might be a way to get started. Another thing is, in your state, do you have support from the state DOT to do some of this stuff? So that's something you can explore, explore with your DOT. So just as an example of that, in Pennsylvania, they had this program called Green Light Go from a few years ago, not for ATSCM specifically, but for various types of signal technology. And I think that they've been working on a resource at the state level to try to help local agencies get things like ATSCM in their systems. Last slide really with content here is, choosing an appropriate, approach to this. So, just to kind of thinking through some of the advantages and disadvantages of some of these efforts. So, cooperative effort, great, as if you've got others you can cooperate with, you can save resources. However, depending on, the pitfalls of that might be, okay, does somebody end up doing all the heavy lifting? Does that cause problems? You need to have agreements and that kind of thing. Kind of just depends on how friendly you are with each other. But again, things to balance which approach you would want to take. Which software to use. So, one option might be trying to use that Utah open source software. The other option is to use some kind of vendor product or to hire somebody to do the development. So again, if you kind of do it on your own, if you've got IT support that you want to use, that's helpful. It may end up being a low cost kind of option for you, but you do have to, maintain that server. You won't have the direct support for the software. It works pretty well, but it's provided as is, it's open source. Whereas if you use a vendor product, then you're going to get that support, and that might be really well, that might work great for you if you don't have IT resources you want to use. But, the trade-off is you're going to have to pay for that support. And, the question is, okay, if you're going to get a system, does that have to go through some kind of procurement process and that sort of thing? And then lastly, thinking about, okay, do I have some interoperability? I don't think that's a big deal these days, but just something to think about in terms of capability of that system you're ultimately trying to get. So I know I'm kind of going through these a little bit fast, but I'm trying to get to the end here. And, the resources here, just the point, I just wanted to point to a couple things that are out there. The examples that I presented earlier and a lot of more examples are both contained in these two reports that were developed as part of a pooled fund study that we had from about 2014 to 2017 or so. And so those are both out there, and you can reach those by these links. So a lot of reading there. Sometime this year, I'm hoping, we've got this NCHRP project, 3.122 is wrapped up, and hoping that report will come out pretty soon. That's going to contain a lot more of guidance on how to do implementations, not only the technological side, but also some more guidance on the usage and the institutional side of things. So I didn't talk about that in great detail today, but there'll be, when that report comes out, there'll be some content in there that'll be really relevant to that. And then thirdly, there's this the Federal Highway Everyday Accounts program. The fourth round of that, ATSCM was part of that. Now they're way past that now, but the resources that they put together are still available out there, and you can reach those by this link, or if you just search Federal, FHWA EDC4, you'll come up. You'll be able to find that link. So I just wanted to get those resources out there, and then last but not least, my contact information, which I've kind of obscured, but let me just fix that real quick. Well, here, I'll just delete that. So my email address, you're more than welcome to contact me if you have questions in addition to these things. That's really what I had to present today, and so that brings us right up to the hour, maybe a minute or two over. So Keith, I don't know if we have any time for questions or not. Yep.
So what I'm going to do, thanks Chris, is we'll go back to the original, whoops. I'm trying to here. There we go. Yes, okay. So if anybody's got any questions, go into the chat pod, chat to all the participants. Chris and I both can see it. You should be able to see your panels. If you can't see your chat panel, there's an icon in the upper right or in the drop-down viewing thing in the left. Go ahead and ask questions. I want to respect your time, so we'll wait a minute or so if anybody's got any questions. As we're doing this, just again, we've got a webinar next week on the 23rd on work zone safety with technologies, smart arrow boards, and temporary rumble strips, and others. 7:31 we have an ethical choices training webinar, and on 8/7 we have working with heated pavements, technical advances. Again, if you came on and you were on for the hour, we'll be sending certificates for those that had registered. If you did not register and you just kind of came on to listen, we don't have your contact information, clearly we can't send that. We welcome anybody to attend. Thank you for attending from all the different time zones. Be safe, be healthy, and treat everyone as an essential being. And that'll be it for today. Have a good weekend, folks. Thank you. Thanks, Chris.
Thanks, everyone.
We'll keep it active here for a bit more if people have questions, but I'm going to stop recording.
Okay.